Okay, so we're continuing to talk about energy and thermochemistry. We're going to pick up in this video talking about the first law of thermodynamics. And the first law of thermodynamics, I've already told it to you, you just didn't know it. It's that energy can either be created or destroyed. So we're going to write that down. Energy cannot be created or destroyed. And so we can write this mathematically, so we can use it more than just words. We're going to define our energy, we already have, but we're going to define it as all energy in a system. So it's going to be all the potential energy plus all the kinetic energy. So all of our energy in a system, because that's we always talk about a system, you can't create any new energy or destroy any energy. And when we talk about it, we're saying everything. So that's kind of funky to think about, because if you define the universe as our system, that means all the energy that we have in our universe has been here from the beginning of time, from the Big Bang. All the energy that we're using to drive our cars, to move our bodies, to make the thunderstorms, to power our cars, it's all been here in one way or another since the beginning of time. I think that's kind of neat. So, as you may be able to imagine, it's difficult. It's easier to measure kinetic energy. It's harder to measure potential energy. We can actually only measure relative potential energy. So, when we're going to talk about energy not being created or destroyed, we're actually going to talk about, can I make this smaller? Let's see, smooshies. We're going to talk about the change in energy. And if energy can't be created or destroyed, that means that if we have a change in energy anywhere in our system, because we can have like I said, if we have a combustion reaction, energy would be released from that system into the surroundings. So energy isn't being lost, it's just being moved from the system essentially to another system or the surroundings. And so therefore our change in energy in our system has to equal our final energy minus our initial energy. And that is a lot easier to measure than just looking at something and saying how much energy is in there. We can take temperature beforehand, we can take temperature afterwards. Temperature is a measure of kinetic energy, and that gives us some idea of the change in energy. So for the first law of thermodynamics, many times we're going to be measured to see. We're going to use this law, this fact that energy can't be created or destroyed but just transferred, to measure changes in energy, and that will become very helpful in our experiments and our analyses. So in the previous slide, when I define all energy, kinetic and potential in a system, the word we use for that, we call that the internal energy of a system. We're going to use E for that in this class. If you take chemistry in the future, sometimes you'll eventually use the letter U for internal energy, but here we're going to use E. So our delta E, is our change in internal energy. And let's look at two examples. And we also said, let me move this down for a sec. We said our change in internal energy in the previous slide is equal to our final energy that we can measure. It's hard to write in a moving car. Minus our initial energy. So you have that written on your paper. So now we're going to look at two examples. Let me make this bigger. Okay, we're going to look at two examples. In this one, we have a reaction taking place in the beaker. I don't know what the reaction is. Could be, let's say, baking soda reacting with hydrochloric acid. This particular reaction is absorbing heat from the surroundings. So heat is coming into it. It needs heat to take place. It needs energy. It won't take place without energy. And it's just taking energy from wherever it can get it, which happens to be the air around it. So it's absorbing energy to make the reaction take place, which makes, because it's absorbing energy, the temperature started out low and then is going up higher as the reaction takes place. So in this example, our final energy is going to be higher. In this particular example, our E final is greater than our E initial, because the system absorbed energy. This was the system. It took energy away from the surroundings. And a way we can measure that is by the temperature. The final temperature of the system, which is the reaction, would be greater at the end than it was at the beginning. So let's take that one step further. I need a new color. Use purple. Remember, our change in energy up here is the final minus the initial. So in this example, our change in energy, we're going to have our final, our T final, or E, well, we'll just use E, minus our E initial. It's going to be a positive number because this is bigger than this. So it's going to be a positive number. So when our delta E is positive, that tells us that our system absorbed energy. If we look at this example over here, on this side we have a combustion reaction. And so our system is what's combusting, the molecules and the things that are combusting. So it's in here. So energy is being released to the surroundings in this example. So at the end, the energy of the surroundings will be greater, but the energy of the system is going to be less. So our final energy here will be less, and again, we're only talking about the system. Our final energy of the system right here is going to be less than the final energy, than the initial energy that it had, total potential and kinetic energy. So if we drew this, if we plug that into the same equation, over here our delta E is going to be a negative number because we have a smaller E final and a big E initial. And so in this case, our delta E is going to be a negative number. When that happens, when you have a change in energy that's negative, that tells you that the system, which again is just the thing that's you're focused on, has lost energy. So these signs are important. We're going to look at them again. So signs are important. We're going to talk about them again in a second, but we just spent some time talking about change in energy and how that is our final energy minus our initial. Now we've also said earlier in the notes that the only way energy can be transferred is either by doing work, I talked about throwing the baseball, or by transferring heat. So we can also write down that delta E, so we're going to say that delta E equals the work done, W for work, plus the heat released, heat transferred, not necessarily released, could be absorbed. So because these are the only two ways we can transfer energy. We can either do work or we can transfer heat. So now we're going to talk about our signs. Signs are very important. They're going to be helpful. Oopsies. So let's look at this table. You should have this in your notes. I'm looking. Do you? Yes, it's somewhere down farther. Q is heat. So if Q is positive, that means the system gains heat. And we just talked about that. And in this example up here, we gave an example with this reaction showing how the system gained heat. And if Q is negative, that means the system lost heat. If work is being done on the system, this is new, we're going to say it's positive. So if I am doing work on a system, if I'm pushing a piston down or doing something to add work, then we're going to put a sign in front of that W here. We're going to say this is positive. But if the system's doing work, if a gas is expanding and pushing a system out, then the work will be negative. So our total delta E is going to refer to the net gain of energy by the system. If this delta E is positive, that means combined these are positive. If this delta E is negative, that means combined these are negative. You're going to work with this concept a little bit more, or a lot more. Okay, let's work this sample problem to make some of these concepts a little more real. So here we have gases A and B, and they're confined in a cylinder piston arrangement just like this. And the red could be gas A, the white could be gas B. They're going to react when they're in here. They're going to react and they're going to form a solid. We're going to say the solid is C. As the reaction occurs, the system loses some heat to the surroundings. So I'm going to lose 150 joules of heat. As they react, the piston will move downward because they're forming a solid. This is an S. So there'll be less volume in here. As the volume of the gas decreases under the constant pressure of the atmosphere, which is the air pressure is out here, so as you have less volume inside, or less pressure inside from less gas, I shouldn't say less volume, less pressure, the air pressure is going to push it down. And as the pressure is putting it down, the air pressure is doing work on the system. The work is 480 joules. So let's calculate the energy change of our system, and we are defining our system as what's going on in here, what I'm circling in purple. So it's asking for the change in internal energy of the system. So we know that internal change in energy is delta E. It gives us, the problem says, well, we lost heat. So I know that I lost heat, so Q equals 1150 joules. And it says I lost heat. The system loses heat to the surroundings. So is that going to be negative or positive? Think about it. It's going to be negative because the system lost heat. It also tells me that work was done, and it says the surroundings did work on the system. So I inserted our table here just to help us out. And this is also, the conventions for signs on work, whether it's positive, negative, I think is opposite from what you use in physics. Although I may be thinking of the pressure times the, well, anyway. So here we have work, W, and work is being done on the system as the atmosphere is pushing the piston down. So that means we're going to say work is positive. So I'm going to write my work down here, and work is 480 joules of work was done, and it's going to be positive. It's being done on the system. Right now we can move this out of the way. So going back to our equation, delta E, if you look at your notes, equals heat plus work. For Q, we're going to substitute in negative 1150 joules. And for work, we're going to substitute in 480, positive 480 joules. So to find our change in energy now, we just have to add these two up. So I'm going to do that right here. I'm going to add this up. If I had a calculator, it would be easier. So I find that delta E is equal to negative 670 joules. So this process was exothermic for the system. The system lost energy. When something loses energy, we're going to define it as exothermic. And when something gains energy, we're going to call it, when the system gains energy, we're going to call that endothermic. Endo for in. System gains energy. Exothermic, so it's going to show up as negative, endo will show up as positive. So I think we're going to end this video here. I'm not sure if I'm going to make another one or just go over it in class.